10. We are in the end game now. This is pretty much the last week of lectures. There is a lecture next Monday, but it's not something you'll be tested on. So this is pretty much the last 2 lectures of main material. In terms of admin, I uploaded like a ton of new videos, so make sure you watch them, especially the bipartite matching and the Eulerian circuits one. And I labeled all these like 6 something, 7 something, 8, etc. I labeled them that way because they are associated with those topics. Like some of the videos are graph theory videos, some of them are greedy videos, but the actual topics covered are relevant to what we're doing now, which is why I kind of waited to release them till now, because now they're relevant. But that's why you'll see they're labeled like that. You didn't miss a video, it's just these are new things that just happen to go with those topics. In addition to that, you've all seen homework 5 already, I assume, but there's also going to be a homework 6. This one's a little weirder because it's only 2 problems, and it also has a shorter deadline, so it's due Tuesday, not tomorrow, but the following Tuesday, 3 p.m. So it's going to be due the day before the final, but pretty much the 2 problems are very indicative of what's on the exam, so my intention here is this will be a very good review for the final exam. Also, the discussion that same Tuesday will be a review session. We won't cover any new topics or anything. It'll just be review. I'll probably also attend that because I wanted to do a review on Monday's lecture, but I'll have like a research meeting after, so I can't. But we'll make sure on Tuesday we have a nice thorough review, so you don't have to worry. And so that's pretty much it in terms of administrative stuff. So any questions about anything up to now? I also noticed homework 3 finally got graded, so that's cool. Hopefully homework 4 will be graded soon as well. So any questions? Okay, so today's the first time we're gonna see like real reductions. So I've kind of tried to explain reductions throughout the course. And we started really small with easy reductions like recursion. And it's easy because it's really clear what you're reducing to. It makes sense that if you could solve the same problem but smaller, you could solve the bigger one with it. Then we got a little crazier and started looking at graph reductions. Here it's not as clear because you're converting your original problem into this graphical model that doesn't necessarily look the same as before. But usually it's pretty straightforward. So these aren't really crazy. You're not like, wow, where did this come from? It usually makes sense that you could model whatever's going on with some kind of graph. But now we're going to talk more and more generally, just general reductions. And for general reductions, it's really confusing. So here, you're converting one problem into another problem that could be completely different. They don't even have to look the same. You could be converting some kind of numerical problem, like subset sum, into a problem like 3 coloring, which is the Christmas party gifts problem we talked about way back in DP. And these problems don't look at all the same. They're completely different in every way. If I told you you could use 3 coloring to solve subset sum, you'd probably think I was crazy, because it is kind of crazy. And so these reductions are way harder because the problems you're using to solve the problem you want to solve is very different in nature. And so you have to argue more thoroughly that these problems are equivalent. So they require stronger proofs. Which is in contrast to like DP, where the proof was kind of obvious. But here we need proofs. Generally, what this will look like is you'll have some problem A and problem B, and you're reducing A to B. So remember from way back in like the first lecture, this notation means A reduces to B. In other words, you're going to solve A using a black box for algorithm B. Using a black box solution to B. And so how do you prove the reduction is actually correct? Well, you have to prove the following. You have to show that A has a solution, specifically an instance to A. So let's say the instance I to A has a solution if and only if f of I has a solution where f of I is an instance to B. Now in general, it doesn't have to be an actual function of I. You don't have to just do it like that. But this is the idea. So you're taking one solution to one problem, converting it into a solution for the other problem, and vice versa. So in particular, there's two directions, and that's the key part. You have to show both directions are correct. Because it could be the case that a solution to B gives you a solution to A that works sometimes. So maybe sometimes that solution works, but it misses something. And so that's why we need two directions. So this is the general template. I'm leaving it a little vague right now because you'll kind of get it just by seeing examples, but overall, when you're doing full reductions, not just simple graph reductions where it's like, what are vertices, you need to be a little more mathematically rigorous with why it works. Okay, so let's see our first example of this. Now naturally, all the reductions today are going to involve max flows, but in general, it doesn't have to be a conversion to a max flow problem. So for the first problem we're going to consider, it's called the edge disjoint paths problem. It's really straightforward. We just want to compute the max number of edge disjoint paths from a vertex S to a vertex T. And what does edge disjoint mean? This just means no two paths in the set you choose can use the same edge. So each edge can appear in at most one path. So what's an example of this? Well, the first example, you could consider this set with the path S to V to W to T, which is highlighted in that blue there. So that's one possible set. Obviously, it's edge disjoint. There's only one path, so there's not two paths to even compare. And the total size of this set is 1. Now, alternatively, we could use this set of paths, which has S to U to W to T and S to V to T. This one has size 2, so obviously it's a better solution to the problem. And also notice this one's node disjoint as well. So not only are no edges overlapping, these orange edges aren't overlapping, but also the nodes used on the path aren't overlapping. So this is an even stronger condition. But we don't need that to be the case. We're allowed to reuse nodes. So here's another example of a set. We have S to V to T. But then we also have this path that goes from S to U, down to V, back up to W, and then down to T. So here the node V is reused. It's in both paths. But none of the edges are reused. Each edge used is still different. And so that's also a valid solution to the problem. Okay. So in general, there are quite a few edge disjoint paths in the graph, but you just care about a single set of them such that they're all pairwise edge disjoint. So your goal here isn't to compute every possible path, it's just a single set satisfying this property. So any questions on what the problem's asking for? Okay, so how are we going to solve this problem? So the first thing you might think to do is use some kind of whatever for search. You're going to walk down the graph, find some kind of path from S to T, then you remove that path, ignore it, and then do that again, and kind of hope that you're going to get a maximal set by doing this. I probably don't have to tell you that that's basically a greedy algorithm, so not really what we want to do. But we can do something similar by using the max flow algorithm. So remember, to compute a max flow, if we use the Ford-Fulkerson algorithm, we look at augmenting paths. Augmenting paths are paths from S to T. And so maybe by using Ford-Fulkerson and choosing capacities in the right way, we'll end up producing a set of edge disjoint paths. So before we can even do that, if we have this as our original graph, we need some kind of capacities, because max flow problems have capacities. So let's just put unit capacities on every edge. So in other words, the capacity of any edge, u to v, equals 1 if u to v is an edge, and it's 0 if u to v is not an edge. Or you can just think of it as the edges that do exist, we just put a 1 as their capacity. And we'll call this new graph with those capacities G prime, or you could just say this is G with this capacity function. Either way, it's the same. So now that we have these capacities, we can just run some max flow algorithm. So let's just compute a max flow. So once we do that, we get some flow out F. And now what do we know about this flow? Well, remember from the flow decomposition theorem, we know that F can be broken down into paths from S to T and cycles. And in particular, the total value of the flow is exactly the number of paths. So why is this? Well, remember, the value of the flow is the net amount that leaves S. And equivalently, this will just be the number of edges that leave S that are saturated. So in this picture here, these are the capacities. And the flow value, maybe it sends 1 down each. So that's going to correspond to the number of paths. So the value of the flow is going to be the number of paths. And also, each of these paths is edge disjoint. So why are they edge disjoint? Well, in particular, remember we have capacities of 1. So if any path uses these edges here, the only way for another path to use that edge is if it sent an additional 1 unit of flow down it, but then we'd break the capacity constraint. This would imply that there's 2 units of flow out of 1, which is impossible. So edge disjointness just comes from the fact that the capacities are a unit. Okay. So essentially what we're doing, we compute the max flow. We know max flows can be decomposed into a bunch of S to T paths. We can just ignore the cycles. We take all those paths. So we just take all these paths. That have unit flow, or let's just say positive flow. And I claim that these give us the solution to the problem. It's a maximum number of edge disjoint paths. Okay. So this is what we're going to do. So why does this actually work? Maybe it's not completely clear why this would actually give us edge disjoint paths. So let's argue about it formally. We're going to have to use the integrality theorem. Spoiler. So I told you last time the integrality theorem is super useful, and we're going to see it used in every single application today. So always remember that. So why integrality theorem matters is here I'm assuming that the flows are all integer, right? If that was 1.5 and 1.5 here, or sorry, 0.5 and 0.5, then it's not a problem, because 0.5 plus 0.5 is 1, and so you could use 2 halves of paths, and it's fine. But because of the integrality theorem, we're always considering an integer maximum flow, because the capacities are all integer, so we know such a thing exists. So in particular, this 0.5, 0.5 thing could never happen. The flow values have to be either 0 or 1. And we'll use that in a second. So let's start with the first case, which is the easier one. So let's suppose G has such a set. So there exists a set of paths P. And the size of P is K. So what are we going to do? We're going to send 1 unit of flow down each path in P. Okay? So clearly the value of this flow is going to be K because there are K edges leaving S. So each path leaves S at the start. So K edges of S are saturated. And that means that the value of the flow, which is the net flow going out of S, is exactly K. So that's pretty straightforward. If there's K paths, they all leave S. They all use different edges leaving S because they're edge disjoint. And so we have a value of the flow that's K. Conservation holds just because we're sending paths of flows. So remember we talked about last time, if you send a single unit flow from S to T, that's called a path flow, and it's always a flow. You have 1 entering every node, you have 1 leaving. So conservation holds because we are taking the union of path flows. And so the last thing we have to consider is the capacity constraints. We have to make sure that we aren't using or going over our limits. So the last thing are the capacity constraints. Why are these fine? Well, it's kind of like the idea I said before. So because they're edge disjoint, we'd have to have the following. So if a capacity was gone over, so let me draw like this. Let's say U to V had L out of 1 capacity where L is greater than 1. Well, by definition, we've sent 1 unit of flow down each path. So the only way for that to happen is if 2 paths shared this edge. This would imply 2 paths shared edge UV. But this contradicts the fact that P is edge disjoint. So that's the first direction. Any questions on the first direction? Okay, so we'll go on to the second direction then. So our new graph G prime, but remember it's just G with capacities. Let's assume it has a feasible flow of value K, and we need to show what the disjoint paths are. So this part's a little easier actually. So if G prime has a flow, specifically an integer flow, which we know exists by the integrality theorem, because the capacities are integers. So because G prime has an integer flow, we have the following ability. When we decompose using the flow decomposition theorem, we know it has K S to T paths. Now all we have to argue are they are edge disjoint. So we already have the paths basically for free because of the integrality theorem and the flow decomposition theorem. So all we really have to do is now argue that they're edge disjoint. So we just define P to be this set of paths. So is it edge disjoint? Yes. The only way for an edge U to V to be used twice. So if U to V is used twice, well, by definition of these paths, they all have one unit of flow. And so this means that this edge had at least 2 units of flow. And clearly that contradicts the capacity constraints. So specifically, this contradicts that F is feasible. Okay? So if we started with a set of disjoint paths, we just send 1 unit of flow down them all, and that gives us a flow of size K that's feasible in our graph G. Otherwise, if I already knew we had an integer flow, if we already solved the max flow problem, then we can strip out all the paths in that flow, and that gives us a solution to the disjoint path problem. And in particular, this K is the same in both cases. And so if we get the maximum flow value, that will give us the maximum amount of disjoint paths. And so solving max flow on G prime gives us a solution, or we should say gives us a max set of edge disjoint paths. In G. Now this is all theory, so what's the actual algorithm? Well, we're going to use Ford-Fulkerson. So we use Ford-Fulkerson to compute the max flow F star. And then how do we actually compute the paths? Well, once we have the flow, we could literally use the flow decomposition theorem and it'll do it for us, but that's kind of overkill for this. So once we have S star, we can just compute S to T paths in the subgraph of G that has positive flow. Once we compute a path, we remove it and then recurse. So we could use flow decomp, but it's sufficient to just use whatever first search, however number of times the flow value is. And this is just because the capacities of each edge are unit, they're just one. So every time we compute a path, we're killing that path. We remove all of its flow value, and so we've reduced the number of paths or the number of edges with flow by 1. So it's the same kind of argument we used for cycle canceling when we were doing the algorithm for flow decomposition. So now what's the runtime of this? Well, we know Ford Fulkerson runs in time O of F star E. But the key thing here is F star will always be small. So notice the cut S to everything else. So the set of S and everything else is a cut. And what's the value of this cut? Or the capacity of the cut is at most the size of V minus 1. Because there's at most one edge from S to every other node. And because the cut size is an upper bound on the flow size, we know this will be O of V times E. And so we can just use Ford Fulkerson to get this fast runtime. We don't even have to use the advanced algorithms. So in particular, we could have just used Orland's algorithm, which is the more advanced algorithm, and then ran the whole flow decomposition algorithm too. And asymptotically, it'll be the same. It'll still be O of V times E. But if you just use Ford Fulkerson and then used whatever for searches to compute the flow, although it's asymptotically the same, it'll be faster in practice because Orland's algorithm is really complicated. It has a lot of overhead. The constant in the O is huge. Whereas Ford Fulkerson, the constant is basically 1. You're doing exactly that much work. So in general, if you can use Ford Fulkerson over the more general methods, try to, because they'll actually be faster. And Ford Fulkerson typically has better mathematical properties because it's very clean and simplistic using the augmenting paths ideas. And essentially, all we really did here is if you white boxed it, if you actually looked at what Ford Fulkerson's doing, it's essentially computing these augmenting paths give us an edge disjoint path. And then we're continuously improving the number of edge disjoint paths we have by using the augmenting paths. So any questions on edge disjoint paths? And your first real reduction in all of its glory. So the actual algorithm is really simple, right? We take our graph, we just create a capacity function, we just throw it in Ford Fulkerson. So at this point, you've done literally nothing. You've given the problem to someone else and they solved it for you. And then all you had to do at the end was search through just do a search over the flow graph, the graph with positive flow edges, and find paths in there. And if you were just asked to find the value or the number of disjoint paths, it's even easier. You don't even have to do this step here. So don't even need if you just want the number of disjoint paths. So if you just want the number of disjoint paths and not the actual paths themselves, then all you have to do is just run Ford Fulkerson basically on the original graph. So you do literally no work at all. It's great. So any questions about this? So in general, for flow problems, they're defined on directed graphs, but sometimes it's really easy to make it work for undirected graphs as well. So for this particular problem, we can compute the number of edge disjoint paths in an undirected graph by converting it into a directed graph and then doing the same thing. So what we're going to do here, this is also a reduction to the directed version. So we're reducing to directed version. So for each undirected edge, u to v, we're just going to add directed edges in both directions. So the edge uv becomes the edge u to v, and the edge v to u. Every single edge becomes a cycle. And so now what can we do? Well, we'll just compute the max acyclic flow in this new graph G prime. So remember, as we talked about last time, when we're doing flow decomposition, really what we did was continuously cancel cycles to create a circulation. And one artifact of that is that you can augment or modify all these flow algorithms to compute acyclic flows, flows without any cycles. Alternatively, you could just compute a normal max flow in this graph and then remove the two cycles. So here, if both of these have flow, you can remove both of them. And it's still a feasible flow. It still satisfies conservation because the amount of inflow to u and the amount of outflow is still equal because there was one going out that we removed and there was one going in that we removed. So we removed one unit going in, but also one going out. So the net change is 0. So if f was feasible before, if it satisfied conservation, it still will. So you can either compute the max acyclic flow or just compute a normal max flow and remove the duplicated edges. And overall, that'll give you a solution to the problem. So what's the final solution? What are the paths? So when we compute this, this will give us a max set of directed S to T paths in G prime. So to get the set of paths P for our original graph, we'll define P to be just the same thing. So if we have a path S, V1, V2, Vk to T, then this will turn into SV1, V1, V2, etc., Vkt. This path goes in our set P. So essentially, we just removed the direction that was enforced in the graph G prime. So we forced it to be directed in order to use the max flow algorithm, and then we just undo the direction. And the key thing here is because there's no cycles, either because we use that little trick or we use an acyclic flow, no cycles implies u to v or v to u can be in a path P prime, so I'll call this P prime, That's the set of paths for the directed version. So one of them can be in there, but not both. And so picking one of them, like converting one of them into the undirected version, is well defined. So our P is well defined. Because remember, originally, the edges are of the form UV without direction. So if we had both UV and VU, we can't really collapse them. It's not the same because we're using that edge twice. That edge turns into two edges. So it's important that only one of them exists in the final flows. Okay, so to do this construction, to create G prime, that just takes O of V plus E time. We just go through the adjacency list and add direction in both ways. So creating G prime is easy. The size of G prime is roughly the same as the size of G, just twice as many edges. And so once we do the reduction to the edge disjoint directed version, the final runtime will be the same as before. So we're running max flow on a graph with just slightly more edges, and so asymptotically the runtime is going to be the same. Any questions? Yes.
If U2V is in one of the paths in the final set, V2U can't be in any path in the final set, right? Because we are calculating like the edge.
Yeah. Right.
Not just on the same path, but it can't be in any path in the final set.
That's correct, yeah. So if U to V is in any of the paths in P prime, then V to U cannot be in any of them because that would form a cycle. We're assuming there's no cycles.
So your P and P prime are not like individual paths for the final set.
Yeah, so each P prime is a set of paths. So this is a set of paths, and this is also a set of paths. And clearly P and P prime have the same size, so it's optimal. Any other questions? Okay. So let's do the same exact thing again, but now with vertex capacities. So in general, we've talked about max flows having capacities on the edges. The amount of things, if you think of the flow network as like a pipe system, the amount of water in any tube is fixed. But each tube, each pipe is connected to maybe say some central area that moves water from one place to another. And up to this point, we haven't capped how much water can enter some plant, some specific area where water is sent and received. So now we want to add capacities to those general places. Not only will the edges have capacity constraints, but also the nodes. So in particular, we'll have these functions, C of E, the capacity for a node. And this is the maximum amount of flow that can go through V. So that's going into V and leaving V. But because of conservation, it's the same thing. So the total sum of flow entering V can be at most C of V. So now we want to resolve the max flow problem with this new added constraint. And we can do it just by reducing to the original max flow problem. So how are we going to do this? So we could think about like changing the algorithm itself. We could change Ford-Fulkerson to consider what happens in the nodes, but instead it'll be easier just to use a reduction. So instead we're going to change the graph itself. We'll change the input graph and then just use the original as a black box. So what are we going to do? We have to somehow translate node capacities into edge capacities, because that's what the original Ford-Fulkerson / max flow algorithms work on. So if you watched any of the recent videos on graph reductions, we actually did this same thing in the videos, but here it is again. So we're going to take a directed edge, U to V, that has a capacity of 5 on U, a capacity of 6 on V, and a capacity of 10 on the edge. And what we'll do is we'll split each vertex into two pieces. So U becomes U in and U out, V becomes V in and V out, and now we just put the node capacity as the edge capacity between the two pieces. So now the node capacity will be satisfied because that edge capacity takes care of it. That edge can't take more than 5 units of flow, and that's representing U taking no more than 5 units of flow. So we're simulating the capacity of a node using this edge, V in to V out. And then all we have to do is solve the original max flow problem on this new graph G prime. And specifically, what's G prime going to be? Well, you're going to have nodes V prime that are V in and V out for each V in the original. You'll have edges consisting of U in to U out for each U in V. The capacity of that U in to U out is going to be the capacity of U. You'll also have edges, which are the original edges, which will be U out to V in. And this is for each original edge, UV and E. And the capacity is going to be the same. So that's the full description of this new graph G prime. So clearly, we've at most doubled the vertices. So V prime, in fact, it's exactly equal. And E prime is going to be roughly, we have one edge per node for the U into U out. And then we also have one edge for each original edge. So E plus V plus E. So overall, V prime plus E prime is O of V plus E. So if we use the original max flow algorithm, the overall runtime is going to be O of V times E. And technically, you want to formally argue why they're equivalent, but this one's kind of straightforward, so I'm not going to do the full proof with the arrows in each direction. Okay, so now we can solve capacities on nodes too. So can we also solve disjoint paths when we care about vertex disjointness? So here, this is the same problem, except each vertex needs to be in at most one path. You can use edges multiple times, hypothetically. Obviously, you can't actually do that because if you visited the same edge multiple times, you've had to hit the same node multiple times. So really, this is a generalization of edge disjointness, or a restriction more. it's an even stronger condition than edge disjointness. So each vertex can appear in at most one path in your set of paths. And what we want to do is reduce it to the edge disjoint problem. So these two problems aren't very different, so we probably could solve one using the other. So how are we going to do that? Well, basically, we're just going to define the capacity of a node to be 1 for all nodes, and then do the capacity of nodes to capacity of edges reduction, and then apply the edge disjoint algorithm. So that's basically all we have to do. So we need at most one path in each set, so we'll just make the capacity of each node to be 1, so it can't be used more than once. Then once we've done that, well, we can just solve the edge disjoint problem in the graph that converted capacities of nodes onto capacities of edges. So why will this correctly be vertex disjoint paths? Because literally the capacity says we can't use that vertex more than once. So it'll definitely be a set of vertex disjoint paths, not necessarily the maximum. So because of this condition here, this implies vertex disjointness, but not maximality. But you can argue exactly like we did before, that if you had a set of k vertex disjoint paths, then you could create a set of k S to T paths in this flow. And specifically, it's now going to be S out to T in paths in the reduced form. Our new source is going to be the out of S, and the new sink is the in of T. This is because in terms of the value of the flow, we want to ignore the capacities on S and T. So visually what this looks like is we're taking our original graph here. We do this conversion. So each node turns into 2 nodes with an edge between them. And then we can take node disjoint paths and just turn it into the same thing, but where we have to use that middle edge for each pair of nodes. And so we can convert a set of node disjoint paths into a flow, and we can do the same thing in reverse. So it's almost exactly the same as edge disjointness once we have this modified graph G prime. So any questions on this? So the running time of this algorithm, all we did was take the original graph, define capacity constraints in O of V time, and then do the edge disjoint or the capacity of nodes reduction, which we know takes O of V plus E. And then from there, we do the original edge disjoint algorithm, which takes an additional O of V times E. So overall, the time is O of V times E. You can also do this for the undirected version too, using the other reduction we did. So you can stack reductions together. There's nothing stopping you from doing that. Okay, so any questions on these? These are kind of the baby problems before we get to the hard problems. Is it already hard? I think the hard problems are more like easy to visualize though. Yes.
What do you mean that the assumption means that you don't achieve maximality, or what the ingredient vertex disjoint?
It implies vertex disjointness, but it's not immediately obvious that it'll be a maximal set of paths.
So it still will eventually be a maximal set of paths?
Yeah, it will be, but that line alone does not prove that.
Oh, okay.
Yeah. But does not imply. So in this particular problem, it's kind of obvious, so you don't really have to prove it, but I would recommend trying to prove it just as an exercise so you can get practice with this template of proof. Okay. So here's one of the first actual interesting problems. So this is called the bipartite matching problem. So if you watched the new videos or if you read all of chapter 4, you've seen this problem before in the stable matching section, which was 4.5. And the original motivation for this problem is you can think of, you have a set of doctors and a set of hospitals, and you want to assign doctors to hospitals, and you want as many matches as possible. So each doctor tells you which hospitals they're willing to work for, and we represent that by an edge from that doctor to that hospital. And similarly, each hospital tells us which doctors they're willing to hire. And our goal is to pick a matching, which is an assignment of doctors to hospitals, that is as large as possible. So in particular, each doctor can only take one job, and each hospital can only hire one person. So what that means is each edge that you pick cannot share any endpoints. So here, for example, let's say U was matched to V and to W. Well, that means Dr. U was given 2 jobs, but Dr. U can't handle 2 jobs, so this is not allowed. On the other hand, this one's fine because they don't share any endpoints. So in general, a matching, you can think of it as a subgraph where each node has degree at most 1. Or if you don't like graph theory, just think of it as each edge doesn't share any endpoints. So for any 2 edges, they shouldn't share an endpoint. They should be intuitively separate. They don't overlap. And our goal is to compute a matching that is as large as possible with the most edges possible. So in the best case scenario, we can create something called a perfect matching. So a perfect matching just says every single doctor gets a job. They're all assigned something. However, in general, maybe one of the doctors is really picky, and so they only have 1 edge, and that causes us to not be able to assign every doctor a job. So not every graph has to have a perfect matching. So our goal is just to compute as big as one as possible. I'll also mention, if you're a little hazy on what a bipartite graph is, it just means you can partition the vertex set into 2 sets L and R, so that edges only go between L and R. There are no edges between nodes in the same set. No edges can be on either side. Okay. So that's the problem we want to solve. This model's like a gazillion problems, so obviously matching one thing to another or creating a maximal set of pairs. This comes up not only in matching doctors to hospitals, but in internships. In biology, you can use this to model certain like reactions in the body. This problem is used everywhere. So solving it is very desirable. And the canonical way to solve it is by using flows. So any ideas how we could solve this using flows? already we have an undirected graph. So at the very beginning, we're going to have to change that. So what would a natural way to direct edges be here? Okay. We can move all the edges from left to right. So the first thing we want to do, we'll take our graph. We have our nodes. And each edge will now direct from left to right. Okay, so that's good. Now intuitively, what do flows tell us? Well, most of the flows we've looked at up to this point have been looking at paths from S to T. Now we don't have any S or T's here, so we should probably add an S and a T. We probably don't want to make anything in L or R in S or a T just because they're basically equivalent. Every node in L is basically the same as any other node. So picking one of them as an S is kind of weird because why choose this node over this one? It's not really clear why you'd do that. So we'll just make two separate nodes, S and T. Now we're already directing things from left to right, so let's just keep doing that. So we'll just have edges from S to everything in L. We'll have edges from R to T. And now this is looking pretty good because if we recall edge disjoint paths, or even vertex disjoint paths, we can create a path from S to T. So let's look at this path from S to T. Now if we picked another path, we want it to be vertex disjoint because it's a matching. So in a matching, we want no edge or no node to be touched by two different edges. And so if we created vertex disjoint paths, that would ensure that no node is touched by multiple edges. And here we can see that any path from S to T is basically picking out a matching. That middle edge there is telling us which edge in the original graph will be in the matching. So the rough idea here is in this graph, vertex disjoint paths satisfy the matching property that no two edges share an endpoint and the middle edge on that matching could then, or the middle edge on that path could then be in our matching. So we could put middle edge in the matching, which we'll call M. And because every middle edge just corresponds directly to an original edge in the graph, this will be well defined. So this is the idea. This isn't literally what we're going to do, but this is what you should be thinking of. Vertex disjoint paths essentially give us matchings in the graph. Now using the full vertex disjoint path reduction is kind of overkill, so let's just do it directly. So each edge can be used at most one time. If it's used more than once, then some nodes use more than once, like we argued before. So we're going to make the capacities of each edge 1 for each edge. And we'll also do that for all of these edges and all of these edges. And so what is this doing for us? Well, this says the amount of flow going into any node U is at most 1. And similarly for any node V over there, the amount of flow going in is at most 1. So in particular, at most one edge can be taken that touches V. And so it will become a matching. So the capacity of 1 on a node, or capacity of 1 on the edge edges touching V imply only one edge touching V can have flow. And that's basically a matching. So overall, this is the construction we're going to do. And you can see every matching, all of these disjoint red edges, can be immediately converted into an equivalent path in this graph. So ultimately what we're going to do, we create this graph, we compute the max flow. We know by the integrality theorem that it's going to be an integer flow, and so every edge is either 0 or 1, and we just pick off the edges that have a 1 there. So our output matching is the set of UV such that the flow from U to V is 1. That's our final output. Now clearly to create this graph, it's going to take O of V plus E time. We just added V at even less than V edges to both sides. So in total we've created V extra edges, 2 extra nodes, and we just direct every other edge. So we can create this G prime. So this G prime, you can create in O of V plus E. And clearly the size of the new graph is also O of V plus E. You haven't drastically increased anything. And so if you ran max flow on this particular graph, it will be O of VE time. And again here I'm using the trick that the size of the flow is going to be at most V. And that's because we have this cut here. This right here is a cut of size at most V. And so we know the flow value will also be at most that cut capacity, which is V. So we can just use Ford-Fulkerson directly because of this fact. And then we just read off the matching. Or if you don't want to read off the matching, we can just, as before, compute paths from S to T and remove one from each path. So any questions on what the algorithm's doing? So the idea is we're using flow paths to simulate choosing an edge in the matching. A single path flow, a unit path flow from S to T, represents a specific choice of an edge in the matching. So now let's prove it correct. So what we need to prove is that G has a matching of size K if and only if G prime has a flow of value K. So what are the implications of this? Well, that means the value of the max flow on G prime is exactly equal to the size of the maximum matching in G. We can convert a matching of size K into a flow of size K and vice versa. So we can't make any larger matching other than this max flow. If we could increase the size of the max flow, we could also increase the size of the matching, and vice versa. Okay, so let's start with the easy case. Let's suppose G has a matching of size K. So what's the flow going to be? Well, the idea behind the algorithm kind of told that, or indicated that for us. So if we have some M of size K, send a path flow S to U to V to T of unit size for every UV in the matching. So for each edge in the matching, let's say this is the edge. Well, what we're going to do is just send flow down that edge and the thing that goes into it and the thing that leaves it. So we just turn it into a single path. So is this a valid flow? Well, clearly conservation holds because it's a path flow. Once again, we send one unit into U, one unit leaves U, and that's true for V as well. So clearly satisfies conservation. The fact that it's a path flow applies conservation. So once again, the main thing here is, are the capacities still satisfied? So are capacities violated? Well, the answer is going to be no, right? So suppose you had some edge. First, let's start with edges of this form, U to V. So if we ever sent 2 units of flow from U to V, that means there were 2 edges in the matching that touched U. This would imply 2 edges in M touched U. Why is that a problem? By definition, they shouldn't share endpoints. This implies there exist 2 edges sharing U as an endpoint. Actually, let me rewrite this slightly backwards. It looks like this. So let's say there was 2 flow leaving U. Then it looks like that. What I drew before doesn't make sense because, by definition, if U was on the left side, well, only one edge by definition goes to U, right? There's only one edge from S to U. There's not multiple. So this case this can't even happen by definition of the graph. Similarly, this can't happen. Neither of these can happen. So the only case that really matters is this one here. This is the only one that could actually happen. And the reason why that won't happen is because it implies some edge is shared. 2 edges are sharing endpoints. Specifically VU and UW. Okay, so this implies that the flow is feasible. Yes?
How can that situation happen?
This one?
Yeah, but you're completely separate matchings. So I get that that's what we're trying to say. That
Yeah.
never happened.
I'm supposing for contradiction that this happens. So if there was ever a point where the capacity was not satisfied, so the goal is to say, are the capacities violated? So assume the capacities were violated. So we sent too much flow down some edge. Well, the only way for that to happen would be this situation. It couldn't happen in the other 2 situations because those edges don't even exist. So either it can't exist at all by definition of the graph, or they can't exist because M is a valid matching. So in either case, we get a contradiction, and so we know that the flow is a valid flow. So we know the flow is feasible. So F is feasible. And now the value of F is K. Why is that? because we've used k edges S to U, where UV was in the matching. So for each edge in the matching, we made a path flow, and in particular, the first edge on that path will add 1 to the value of F. So in the picture here, each of these in red have flow value 1. So for each edge in the middle, we know there's an edge that goes into it to satisfy conservation, and so that adds 1 to the value of the flow. So the value of the flow is exactly equal to the value of the matching. Okay. So now for the other direction, let's suppose you had the flow. What's the matching? So let's say G prime has a flow of value k. And again, I'm going to use the integrality theorem here. It's critical that every edge is either 0 or 1 flow. So we're almost always going to be using this integrality theorem. Even if I don't say it out loud, think to yourself, should I be using the integrality theorem here? And if the answer is yes, make sure you write it down on whatever problems you're working on, because it's an important assumption. It does not hold that the capacities are not integer. So it's very important here that we've been using integer capacities. Like the capacities are all 1. If I made the capacities 1.5, integrality does not hold, and none of this works. So it's very important. Okay, so if we have a flow of value k, well, we know either by flow decomposition or just by looking at the graph, but just to be very formal, I'll say by flow decomposition, F is a sum, or you could say it's a union, it's a combination of S to T paths. Now here there's no cycles. We don't even have to consider that because our graph is a DAG. It's a directed acyclic graph. All the edges go left to right. There's no back edges. So we don't even have to consider cycles in this problem. And so we have a bunch of S to T paths, and I claim the middle edge on each path gives the matching. So basically the idea we use to create the algorithm is just becoming the proof. So what are we doing? Well, our matching M is the set of UV such that the flow from U to V is 1. Now clearly this is size k. If the value of the flow is k, then we know there's k S to T paths, and there's k middle edges on the k paths. So size of M equals k is pretty obvious. Why is it a valid matching? Well, suppose there were 2 edges, U to V and U to W. So for this to happen, we would need the flow. So this is both 1 unit of flow. But what has to enter U? We would need the flow from S to U to be 2. That's a contradiction on the capacity. Or maybe it looks like this. We have it in the other direction, so we have U to V, W to V. These are both 1. But now the issue is this is 2 out of 1. I'm saying it's equal to 2, but really this is just greater than 1, which is the point. Right? So these are the only 2 ways that M would not be a valid matching. So this is the case when UV and UW were in M. That's the assumption that we're trying to contradict. And in this one, we have UV and WV is in M. We get contradiction. Okay? So the matching we compute in this way is a matching. It is correct. No two edges will share an endpoint. And then, yeah, and it's O of V times E in total. So any questions on that? Okay, I'll move on to the next one then. So tuple selection is just a generalization of bipartite matching, but instead of bipartite, it looks like this. So we have multiple segments, basically. And the way you want to think of this is you have D resources, each from a different set, x1 through xd, and you want to find a maximum set of D tuples. So you want to pick one of each resource, and you want to pick as many of these D tuples of resources as you can. Now, of course, this would be trivial if you could pick all of them, but there's going to be restrictions. So for each index I, an element x and xi can appear in the most C of x selected tuples. For each index I, and if you have two elements x to y in adjacent pairs, you can have C of xy selected tuples. So before, for the bipartite matching problem, C of x was 1 for matchings, and C of xy was either 1 or 0, depending on whether the edge existed in the graph or not. So that's the idea here. So we're just generalizing that. So now maybe we would allow some nodes to be used a couple times. So instead of forcing it to be used at most once, we say we can let a few things share that node. Or maybe we have a couple edges we'll allow to be used multiple times. And in general, this will represent an assignment problem. So we're assigning one thing to another thing, to another thing, to another thing, to create one total assignment of multiple items. So there's this general way to do this that looks like this, which I will just ignore for now because it's not very clear why that matters. So let's look at an example to see where this comes from. So you might remember from the greedy chapter, there was this course scheduling algorithm where we sort by the finish times. And I said that works for very basic course scheduling, but for real course scheduling, like what universities do every day, you have to use a max flow algorithm. And so this is that max flow algorithm that UW-Madison has used to assign us this room at this time. So what's the goal of this problem? So in this one, we're thinking of scheduling final exams. So we have to pick a room, a time, and a proctor for final exams of every class. And here there are n classes. So our given input, we have an array, E, that represents the number of students enrolled in the ith class. We have an array S that represents the size or the number of seats in the rooms. So in particular, you can't assign a class to a room if the number of students enrolled is bigger than the number of seats. So that's a key restriction. And then we also have an array that indicates whether a proctor is available at time L or at time K, and there are a bunch of proctors. There's P total proctors. So for each proctor, we need to know what times they're available at. And that's what that array gives us. And then the total size of the input is just the total size of all of these. And our goal is to create an algorithm that picks a room, time slot, and proctor for every final exam, or reports that it's impossible to do that. So one example where it's impossible is, let's say you have 1 million classes in 2 rooms and 1 time slot. Obviously, that's not going to work. So it's very possible that a solution to this is infeasible. And oftentimes it is. So usually, real universities, the requirements they have are too restrictive, and so you can't solve the problem. So up here I said it's important that the constraints are adjacent, which means they go between 2 resources. If you added even a single edge from one resource to another that isn't next to each other, the problem is unsolvable. So yeah, it's very important, very critical assumption. Okay, so how should we go about solving this? Well, we're doing an assignment problem, which is like a matching problem. And so for matchings, we just directed the edges from left to right. Now we just have more groups, so why don't we just do the same thing, right? So we're basically going to do the same thing. The picture will look like this. So it's exactly the same as bipartite matching, but instead of 2 things, you just have more and more and more. But the reduction will be the same. So this is the actual graphical model we'll use. So we have one group, which is classes, because we're assigning an exam for each class. Each exam has to be held in some room, so we have to pick a room. And you can think of this as a step-by-step process. First, you pick the class you want to figure out where to put. Then you want to pick the room. Then you want to pick the time. Then you want to pick a proctor. That's how you should think about this. It's a sequential process. We're doing it one by one. So overall, we end up picking 4 items, but at each moment in time, we only have to think of connecting one of them to the next one. Okay, so what is this modeling? So this is modeling the fact that each class has one final exam. This constraint here indicates that there's no restrictions on the rooms other than the fact that they fit. So we have an edge. Yeah, so we have an edge from a class to a room only if the enrollment for that class is at most the number of seats in that room. But otherwise, we really don't care about the specific numbers or anything. So that's why it's an infinite capacity. It's basically a yes or no question. Either we can fit in there or we can't. The number there doesn't matter, so we just make it infinity. Give us the most options. Now for rooms and times, each room can be assigned exactly 1 time. You can't have multiple classes in the same room at the same time. And you also can't have one exam split between 2 times. You don't want to move rooms mid-exam. So that's what this 1 is indicating here. So it says, we don't care which room gets which time. And so there's all possible edges. So long as it's feasible. I.e., 1 exam per room per time. We don't split exams And we also don't, let me say and, place two classes in the same room. At the same time. So that's why that 1 is there. Exactly one course can be at this room at this time to avoid this bad stuff there. Okay, so the last one says each time we need a proctor. We need one proctor for each time. And in particular, we only have edges if the proctor is available at that time. So here is where that array A of KL is coming in. We only have an edge from time K to proctor L. So this turns into, if this is true, we have an edge from K to L. So if proctor L is available at time K, we have an edge from K to L. And again, this is 1 because we can only have the proctor, we only need one proctor in one room at a time. And the last one says each proctor can watch at most 5 total exams. So we don't want to overwork our proctors, so we have a hard limit there. So this is the full graphical model of this problem. So we've picked our resources from left to right, and we designed the capacities and the edges to represent our restrictions in the problem. So each of these edges, whether they exist or not, and the particular capacity we give it, are modeling some aspect of the problem. So to summarize, this is a 1 because each class has one final. For each class, you need to pick a room for the final. We don't care which room, so long as the room's big enough. Then, for each room, we need to pick a time, exactly one time for that particular class to have the exam. We don't want more than one exam to be at the same room at the same time. Then this one here represents a proctor can reasonably proctor that exam at that time. And then the last one says this is the total amount of times a proctor can be used. So overall, this will tell us whether we can do the assignments or do the scheduling or not. So the final algorithm is we compute G prime, then we compute a max flow in G prime from S to T, in ST flow. Specifically, this is S prime T prime, just because S and T are used in the problem in different ways. Okay, so we compute the max flow, and now what do we have to do? So we have some max flow F star, and the goal of the problem, remember, is to say whether it's possible or not. We just want to see, is it possible to schedule? So how do we know if it's possible to schedule? Is there a nice, easy criteria we can check? If I give you the flow, how can you tell me if the scheduling was possible? Yes?
If the outflow from S is equal to the inflow from T.
So that will always be true. That's just by definition of flows.
The number of paths is equals to the number of classes.
Yep. So we need the value of F to equal N, the number of classes. Why? Because remember, each path in this graph represents an assignment of a course to a room to a time to a proctor. So if we were able to find N paths, that means we found N possible assignments that were valid. And because there's only N classes, that means we found an assignment or we found a schedule for each class. So if this happens, then return true. else return false. And this is because each path from S to T represents a valid schedule for one course. Just like before, a path from S to T represented a valid matching edge, we're just generalizing that idea one more. The paths are just longer now. So overall, what's the running time of this algorithm? Well, again, we have this nice property that we have this cut here. This is a cut of size, at most the size of V. And in particular, not only is it the size of V, it's the number of classes. So the size of V is much bigger than the number of classes. But just the number of classes alone. So the value of the flow is at most n. And so we can compute this thing in O of n times the number of edges. Now what's the number of edges? It's going to be capital N squared. Because we have capital N represents all the resources, and we're possibly pairing all the resources. So each pair, each set of edges here, could be possibly order n squared. And so this is O of n, capital N squared. Or you could just say it's O of n cubed. That's fine too. Because of course, little n is at most big N. But this one's the most precise. And Jeff doesn't do it in the textbook. It's so sad. Yes?
Why is the number of edges at most big N squared?
So in total, we have big N resources. And for any two resources, the total number of pairs between them, which is the total number of edges between them, is at most the square between them. So it's, for times and proctors, you'd have like T times P.
We can define a tighter bound, right? Like the classes are not, the classes don't have an edge between like classes and times or classes and proctors, right?
Yeah, you can make a tighter bound for sure. I would recommend not doing it though. It gets pretty complicated with the algebra. But in the worst case scenario, it will be roughly n cubed anyway, so it doesn't really save you anything. But you can definitely do it. Okay, so now that we have an example, let's go back to the general framework. So the general framework here is we represent each resource or each thing we want to select as one of these groupings. It becomes a set of nodes in our graph. So G contains a vertex for each element of a set Xi. It has the vertex S and T, and the capacity of each of these nodes is C of X, which is just the original constraint on the nodes for the given problem. So actually in this problem for course scheduling, we didn't really have capacities on nodes, right? What does it mean to have a capacity on a course? It doesn't really make sense in this context. So you could think of that as just giving it infinite capacity. Or you could just not define them. Either way is fine. And then we also have edges from one resource to the next one, but only between pairs. We don't have edges to the later ones. So this would not exist. And the capacity of these edges is exactly the capacities or the restrictions we had for pairs of resources. So here it's kind of obvious what to do because it's set up in a way to where you would just do it like this. But for course scheduling, you have to think a little more of how you're modeling it. And in general, what's difficult about these problems is first getting it into this form. Once you can model it as this tuple selection problem, then it becomes pretty easy. Because all you have to do is compute a max flow, and then use a flow decomposition to figure out all the paths, which give you a valid tuple. And then this is the final result. So any questions on course scheduling? It's much harder than the original greedy algorithm, right? That's because the original one doesn't work for general problems. Okay. If there's no questions, we'll move on to the last example, which is really weird. So up to this point, we've focused mostly on calculating a max flow in order to find some kind of path. That's been the pattern. But remember, max flow min cut theorem says the two problems are equivalent. You can solve the max flow problem or you can solve the min cut problem. So in this application, we're actually going to compute a minimum cut instead to solve whatever problem we want to solve. So this problem's a little weird to kind of write down in words, but I think it's intuitive. So the idea here is you have a set of projects you want to solve. Each project gives you some profit, $sign of V. This is the profit function. And your goal, of course, is to figure out a set of projects to maximize your total profit. Now, the key thing here is some projects have a negative profit. So not every project is immediately worth your while, but projects have dependencies. So maybe you want to do this project, the one that gives you 6 profit, but in order to do that project, you first have to satisfy some kind of prerequisite project. So in general, let's take this one as an example, this column right here. So maybe the minus $8 represents you're buying a computer. So before you can make an application that will make you $3, you first have to buy a really expensive computer. So before you can do that project, you have to complete that project. So, naturally what we want to do is just pick all the positive projects. Those are the ones that give us profit. But we can't just pick them because before we pick a project, we have to make sure we've satisfied all the prerequisite projects. So you're very familiar with this because in university, before you take the classes you want to take, you first have to take all the sad, miserable classes you don't want to take. So you could think of those as being this here. You first have to solve the -2 project, which is like maybe CS200, before you can take the +4 class, which is maybe algorithms or OS. Okay, so that's kind of what we're doing here. The goal is to pick a set X of projects with maximum profit such that each prerequisite is satisfied. So if you pick project 4, you have to also pick -2 and -3. You have no choice. So it's a very natural problem. The question is, how do we solve this? If we're given this graph as the input, this dependency graph. So the idea here is that we want to partition the projects into 2 groups, S and T, where S is the jobs we select. These are the jobs we want to do. And then T is the set of jobs we turn down. So maybe in this example above, we pick job 4 and -3. We also pick jobs 6, 2, and -5, but we don't pick the last column. We don't take job 3 and -8. Okay? So if we did that, what would our total profit be? So our profit's going to be 4 plus 6 plus 2, -3, -2, -5. So 12 minus 10, which is 2. So overall, we do make a net positive profit. Now, of course, if everything was negative, what would we do? Do no projects. We do no projects at all and get a 0 net profit. You never want a negative profit. So this is the idea we want to do. Pick some subset of jobs that we want to do and pick some that we turn down. And so we're modeling this as an ST-cut problem. So we're modeling this as computing an ST-cut. The only problem is we can only solve for minimum cuts, but we kind of want like a maximum cut, right? We want to maximize our profit. So how do we do that? Like how do we enforce prereqs? How do we use minimum cuts to solve this problem? How do we convert negative profits into capacities, right? So in the min cut problem, we only have capacities, and those are always positive. We don't have any sort of notion of a negative capacity. So, how are we going to do this? So first thing you want to, oh, you have an, okay.
Random guess, but can we just multiply every value by -1?
To make capacities, yeah. So that's a thing you can always do. So we could turn these into capacities by just taking the negative versions, or the absolute value.
Oh, but it's not on the edges.
Yeah. So the first thing we should do, I mean, we're given a graph with the dependencies, so we should probably build off of this graph. So why don't we just take the dependency graph as is? It's a flow problem, so we probably want an S and a T, so let's just make an S and a T that connects to everything, kind of like how we did for bipartite matching. These will have edges to everything else. These will have edges from everything else, etc. So just mechanically, we can probably guess it's going to look something like this, right off the bat. So now, how do we make capacities? Well, we have positive profits. We could just make those capacities instantly. We could turn the negative profits into a capacity by looking at their absolute values. So we could come up with some kind of capacities like this. And then this is 6 and 2. So we could do that. So now we have a graph with capacities. We don't really care about these. We'll just make these infinity. Okay. Now so far what I've just done is kind of messed around with a picture. None of this really has meaning. I'm just like trying stuff, right? We had negatives, we just made them a positive the easiest way we could. We had positives, we just kept them. We just moved them onto the edges. Now what's really interesting is that's exactly what you should do. So what I just described actually will give you a valid algorithm to solve the problem. Now the reason it works is really wacky, but it does work. So what are we going to do? We're going to define our capacities. We'll have an edge from S to V with a positive capacity for every profitable job V. So if $sign of V is positive, we're just going to make that the capacity of the edge from S to V. Otherwise, if it's negative, then we're going to make the edge go from that node to T instead. And we'll just take the negative of it as the capacity. And at the very end, we don't really care about the edges between jobs, so we'll just make those infinity. So this is what it looks like. Here's the picture. So each of these jobs, the ones that were not profitable, they had a negative profit. We just negated them to become the capacity. And we made an edge to T. On the other hand, the things that were profitable, like 3 here, we made an edge from S to that project of value 3, of capacity 3. Okay, so we have a graph now. We just did the most basic things we could to translate the original graph into a flow network. But now what should we do? Well, I don't know. Let's just compute a minimum cut. Whatever. We don't care. Just compute a minimum cut. So let's compute a min cut. In this graph G prime. So cool, we have a min cut. Now what do we do with the min cut? This is the weird part. Now remember, the idea is that S represents the jobs we want to take, and T represents the jobs we're going to reject. So what we want to do is we want to just return the set S without little s. Because remember, little s is something we added to the graph that's not part of the original problem. So S without little s, this is a valid set of projects. Now what's not clear is that this project set will satisfy prereqs or that it's even profitable. So does it satisfy prereqs? Is it profitable? Well, first of all, it's fast. Like, we've done this in O of V times E time, assuming we use, say, Orland's algorithm and then a flow decomposition. We don't even need the flow decomposition. We just return S. So that's the benefit of not using paths. It's even easier. So it's fast to do this process. But let's first think about, will it satisfy prerequisites? So the first thing to notice is these infinite edges are very important. So let's say we chose a cut with the following structure. Let's say we chose 3, but we did not choose -8 and -5. So in particular, what that would look like, it means S contains that node, but T contains the rest. So this is T, and this is S. So here's an example of a cut that would not have the dependencies satisfied. We try to complete project 3 without first completing its prereqs. But the key here is, what's the capacity of the cut? So the capacity of this cut, S to T, is at least the capacity of the edge from 3 to -8. Right? And what's the capacity of that cut? It's infinite. So if you did try to weasel out of using a prerequisite, you'll instantly get an infinite solution. On the other hand, when we tell you a trivial cut that has smaller value, what if we just make S every project? So on the other hand, if S equals every project, then the capacity of the cut, this is going to be exactly these numbers here. So the only edges going between S and T are the edges from things to little t. So if S is every project, well, that implies that T is just little t. And so the capacity is just the sum of all the negative projects. So it's going to be, it's not optimal. It's going to be 2 plus 3 plus 5 plus 8, but that's still less than infinity. So if you ever try to not satisfy prereqs, you'll instantly get an infinite cut. And because you're computing minimum cuts, you'll never do that. So you're always guaranteed that prereqs are satisfied. So this is yes, because cut is minimum capacity. Otherwise, get infinite. Okay. So we know it is a valid selection of projects. Now the question is it truly the max profit or not? So clearly this one here is not at all max profit. It's the min profit. You only took very, very bad jobs. Well, you took all of the jobs, and so you're also taking all the very bad jobs. So we need to prove something about the profits here. Now, I'll tell you immediately the capacity of the cut is not equal to the profit. How could it be? It's a positive thing. Profits could be negative. So what really is going to happen here is the profit of our set S is going to be something minus the capacity. And because it's minus the capacity, minimizing the capacity of the cut corresponds to maximizing the overall thing. So in particular, we're going to define P here. P is going to be the total profitable jobs. So for every job that gives you some positive profit, we're just going to sum up its profit. So in a perfect world where you didn't have prereqs, this is what you would get. So this is if no prereqs. So in an ideal world, you just skip all the prereqs and you just take the things that are profitable. That's what P stands for. So think of P as the total possible profit in a perfect world. So then what this says, this lemma here says that the total profit of S is the total profit ever possible minus the capacity of the cut. And so if we minimize the capacity of the cut, we're maximizing that net difference, which is our profit. So to do the proof, we also need two other definitions. The cost of X is the sum of all the negative profit items in X. So it'll be the sum of all these capacities from U to T. The yield of X, you can think of this as the positives you get. So this is all the positive profits of their profits, which is the sum of all items in X of the capacity from S to V. And then finally, the profit of a set X is the yield of X minus the cost of X. So it's how much all the positive profits we get minus all the negative profits we get. So this is just a way to convert back, because we took negative profits and we made them positive to make them capacities. So this way it just converts it back. It adds the negative back. Okay, so any questions on these definitions? So basically it's just the intuitive idea of your profit is how much you get minus how much it costs you. It's just now we're relating how much you get and how much it costs you to the capacities of our graph, G prime. Okay, so the proof is actually not too hard. So the first thing to notice is that P is the yield of all of V. So over all the vertices, it's the total yield. Because by definition, the yield is the sum of all the positive profit things. And now the yield of V, well, this is just the yield of S plus the yield of T, right? So we have a summation, and we've regrouped the terms into one side and the other side. So this is just saying the sum of all profits in S plus the sum of all profits in T. That's equal to the sum of all profits in S union T, which is equal to V because it's a partition. That is a U. And there's also a max in all of these. But that's why. We're just splitting up the summation. Okay, so we want to argue about P minus the capacity, but what's the capacity? So let's look at the picture. So the capacity of a cut, it's going to be the sum of edges of things that are costly plus the sum of edges of things we didn't take of things that are profitable. So that second one's a little easier. So that's the yield of T. Right? So that's the sum of all the positive projects. These are all the positive projects that we did not choose. Since we did not choose them, it crosses the cut. On the other hand, everything we did choose, their negatives are what appears in the term. So this is the cost of the set S that crosses the cut to T. So every edge either is a costly thing that we did choose, or it's a positive thing that we didn't choose. And so the capacity of the cut is the yield of T plus the cost of S. Okay? So now what's the difference? Well, P minus the capacity is going to be the yield of S plus the yield of T minus the yield of T and minus the cost of S. And so these two terms are going to cancel. And so we're left with the yield of S minus the cost of S. But by definition, that's just the profit of S. And so we get exactly what we wanted. The profit of S is exactly the difference between the best possible profit in a perfect world and the capacity of the cut. Okay? And so this implies the algorithm's correct. Minimizing the cut will maximize our profit. And from our argument before, it's a feasible project choice because prerequisites are always satisfied. And overall, the running time, just like in all these other applications, G prime is going to take O of V plus E to construct. The size of G prime is roughly the same as the original. So if we run max flow on this graph, it'll just be the same running time as on the original graph. So the time is O of V times E. And this time we have to use Orland's algorithm. We cannot use Ford-Fulkerson this time because the cuts and the flow could be very large. We don't know. Maybe you can get a lot of profit. So we can't just use Ford-Fulkerson and say, well, there's a small cut, because there might not be a small cut. Whereas in the other applications, the reason we can use Ford-Fulkerson is because we argued there was some small cut, and so if we compute the max flow using Ford-Fulkerson, the running time will be small as well. So in particular, this is also true for the tuple selection. Tuple selection in general also needs Orland's algorithm because those cuts could be very large capacity, the flows could be very large. In course scheduling, we got lucky because the number of courses happened to be small and the capacities were small. Okay. That's everything for today.